Okay. Short stream today, I guess. I'm gonna try and get this section done. So, in the previous section, we saw limits that were at infinity, and now it's time to take a look at limits at infinity. By limits at infinity, we mean one of the following two limits: the limit of f of x approaches infinity, or negative infinity. In other words, we're going to be looking at what happens to a function if we let x get very large in either the positive or negative sense. Also, as we'll soon see, these limits may have infinity as a value. First, let's note that the set of facts from the infinite limit section also hold if we replace the limit of x, the limit as x approaches a constant, with the limit of as x approaches infinity, or the limit as x approaches negative infinity. Proof of this is nearly identical to the proof of the original set of facts, with only minor modifications to handle the change in the limit, so it is left to you. We won't need these facts much over the next couple of sections, but they will be required on occasion. In fact, many of the limits that we're going to be looking at, we will need the following two facts. 1. If r is a positive rational number and c is any real number, then that's true, I guess. Yeah, cause it's approaching 0, yeah. And the same if it's negative. The first part of this fact should make sense if you think about it, requiring that r is greater than 0. We know that x to the power of r will stay in the denominator. Next, as we increase x, then x to the power of r will also increase. So we have a constant divided by an increasingly large number, and so the result will be increasingly small, or 0. The second part is nearly identical, except we need to worry about x to the power of r being defined for negative x. This condition is here to avoid cases such as r equals half. If this r were allowed, we'd be taking the square root of negative numbers, which would be complex, and we want to avoid that at this level. Note as well that the sign of c will not affect the answer. Regardless of the sign of c, we'll still have a constant divided by a very large number, which will result in a very small number, and the larger x gets to the smaller the fraction gets. The sign of c will affect which direction the fraction approaches 0, i.e. from the positive or the negative side, but it still approaches 0. If you think this is really a special case of the last fact from the facts in the previous section. However, to see a direct proof of this fact, see the proof of various limit properties section in the extras chapter. Let's start off the examples with one that will lead us to a nice idea that we'll use on a regular basis about limits at infinity for polynomials. Okay, so we got example 1. Part A. The limit as x approaches infinity of 2x to the power of 4 minus x squared minus 8x. Okay, so first thing. Well, there's two ways you could do this, I guess. You could just plug it in infinity. Minus infinity squared minus 8 infinity. So really, this number doesn't matter, front, or this number. So we got infinity to the power of 4 minus infinity to the power of 2 minus infinity. And you only care about the highest exponent. And since it's a positive infinity, and it's an even, well, even if it was odd, it would still be positive, so the answer is positive infinity. Or you could just look at the biggest exponent, so 2x to the power of 4, and do the same thing, plug in infinity. The 2 in front doesn't matter. It's positive infinity, even exponent, so it's infinity. So the website says, our first thought here is probably just to plug infinity into the polynomial and evaluate each term to determine the value of the limit. It is pretty simple to see what each term will do in the limit, and so this seems like an obvious step, especially since we've been doing that for the other limits in the previous sections. So let's see what we get if we do that. As x approaches infinity, then x to a power can only get larger, and the coefficient on each term, the first and third, will only make the term even larger. So if we take a look at what each term is doing and the limit, we get the following: an infinity, a negative infinity, and a negative infinity. Now we've got a small but easily fixed problem to deal with. We are probably tempted to say that the answer is 0 because we have an infinity minus an infinity, or maybe negative infinity because we're subtracting 2 infinities off of 1 infinity. However, in both cases we'd be wrong. This is one of those indeterminate forms that we first started seeing in a previous section. Infinities just don't always behave as real numbers do when it comes to arithmetic. Without more work, there is simply no way to know that infinity minus infinity, what infinity minus infinity will be, and so we really need to be careful with this kind of problem. To read a little more about this, see the types of infinity section in the extras chapter. So we need a way to get around this problem. What we'll do here is factor the largest power of x out of the whole polynomial as follows. Okay, let me try that. I remember seeing this before, and then it didn't really make sense, and I watched that video and it kind of did. So they factor out the highest exponent, and they get 2 minus x what would it be? 1 over x squared, yeah, minus 8 8 over x to the power of 5. Wait, no. X to the power of 3. Let me see. Yeah. If you're not sure you agree with the factoring above, there's a chance you haven't really been asked to do this kind of factoring prior to this. Then recall that to check, all you need to do is multiply the x to the power of 4 back through the parentheses to verify that it was done correctly. Also, an easy way to remember how to do this kind of factoring is to note that the second term is just the original polynomial divided by x to the power of 4. This will always work when factoring a power of x out of a polynomial. Now for each of the terms we have okay, so they split it up. The limit x to the power of 4 as x approaches infinity equals infinity. And the other one (2 minus 1 over x squared minus 8 over x cubed). I guess if you solve this, or no, the x to the power of 4 wouldn't be here. It would just be this, because we're splitting them up. Okay, so if you plug in infinity, this approaches 0. This approaches 0. So you have 2. Infinity times 2. So it's just infinity. The first limit is clearly infinity, and for the second limit, we'll use the fact above on the last two limits, last two terms. Therefore, using fact 2 from the previous section, we see the value of the limit will be infinity. Let me see what fact 2 is. It's probably just like something times infinity is infinity. If L is greater than 0, what's L? Oh, the answer of the limit of g of x. It's x approaches c. Then the limit of infinity, basically infinity times a positive L is going to be infinity. And then for 3, infinity times a negative L is going to be a negative infinity. So yeah, pretty much what I thought. And then B, okay. So doing it the same way they did it, I'd want to factor out the t to the power of 5. So it'd be 1/3 plus 2 plus 2 2 over t power of 8. No. T squared? Yeah. Minus t cubed? No. Minus 1 over t cubed plus, oh wait, there's an 8. Oh wait, you can just do 8 over t to the power of 5. I think I did that in the last one. Yeah. I don't know why that threw me off. Okay, so we got the limit of t to the power of 5 as t approaches negative infinity equals negative or wait. Okay, it's an odd exponent. So yeah, it would still be negative infinity. Then the limit of 1/3 plus 2 t squared minus 1 over t cubed plus 8 over t to the power of 5. This approaches 0. This approaches 0. This approaches 0. Oh wait, as t approaches negative infinity. So this equals 1/3. Negative infinity times 1/3 negative infinity. We'll work this part much quicker than the previous part. All we need to do is factor out the largest power of t to get the following. Did I get the same thing? Seems like it. Remember that all you need to do to get the factoring correct is divide the original polynomial by the power of t we're factoring out. T to the power of 5 in this case. Now all we need to do is take the limit of the two terms. And the first, don't forget that since we're going out towards negative infinity, and we're raising t to the 5th power, that the limit will be negative. Negative number raised to an odd power is still negative. In the second term, we'll again make heavy use of the fact above to see that this is a finite number. Therefore, using a modification from the facts section, the value of this limit is negative infinity. Okay, now that we've seen how a couple of polynomials work, we can give a simple fact about polynomials in general. Fact 2. If p of x equals all that, then that is a polynomial of degree n. Then, wait, what? What this fact is really saying is that when we take a limit at infinity for a polynomial, all we really need to do is look at the term with the largest power and ask what the term is doing and the limit, since the polynomial will have the same behavior. You can see the proof in the proof of various limit properties section in the extras chapter. Let's now move into some more complicated limits. Evaluate both of the following limits. So the limit of 2x power 4 minus x squared plus 8x over negative 5x to the power of 4 plus 7. This is x approaches infinity. Okay, so doing the same trick. Factor out an x to the power of 4. I guess on the top and bottom. Two minus 1 over x squared plus 8 over x cubed x to the power of 4 minus 5 plus 7 over x to the power of 4. Okay, then you can split these up by division. The limit of x to the power of 4, 2 minus 1 over x squared plus 8 over x cubed. As x approaches infinity. And then you don't really, this part over here is just going to be 2. Times a positive infinity, so and then the bottom, the limit of x to the power of 4 minus 5 plus 7 over x to the power of 4. This goes to 0. So we've got negative 5 times a positive infinity, so that's going to be a negative infinity. So we got a positive infinity and then a negative infinity. So that's going to be, should be negative infinity. First, wait, did I do? No, I only did positive infinity. So if I did negative, what would change? They'd still split up the same, right? Yeah. So this would still be positive infinity because it's an even exponent. The bottom would still be negative, they'd be the same thing. First, the only difference between these two is that one is going to positive infinity and the other is going to negative infinity. Sometimes this small difference will affect the value of the limit, and at other times it won't. Let's start with the first limit, and as with our first set of examples, it might be tempting to just plug in the infinity. Since both the numerator and denominator are polynomials, we can use the above fact to determine the behavior of each. Doing this gives... Okay. This is yet another indeterminate form, and in this case we might be tempted to say that the limit is infinity because of the infinity in the numerator, 0 because of the infinity in the denominator, or -1 because something divided by itself is 1. There are 3 separate arithmetic rules at work here. And without work, there's no way to know which rule will be correct. And to make matters worse, it's possible that none of them may work, and we might be given a completely different answer, say a -2/5, to pick a number completely at random. So when we have a polynomial divided by a polynomial, we're going to proceed much as we did with only polynomials. We first identify the largest power of x in the denominator, and yes, we only look at the denominator for this. We factor this out of both the numerator and the denominator. Doing this for the limit gives once we've done this, we can cancel the x to the power of 4 from both the numerator and the denominator, and then use fact 1 above to take the limit of the remaining terms. Oh. So wait, instead of just doing that, the dude just says, don't even split it up. Just cancel this out. Oh, I see. Bro was like, I'm gonna pick a number completely at random, -2/5. Oh, by the way, the answer is -2/5. In this case, the indeterminate form was neither of the obvious choices of infinity, 0 or -1. So be careful with making these kinds of assumptions with this kind of indeterminate form. The second limit is done in a similar fashion. Notice, however, that nowhere in the work for the first limit did we actually use the fact that the limit was going to positive infinity. In this case, it doesn't really matter which way the infinity is going, since we get the same value. In the previous example, the limit that we were using in the limit didn't change the answer. This will not always be the case, so don't make the assumption that this will always be the case. Let's take a look at an example where we get different answers for each limit. So the limit of square root of 3x squared plus x over 5 minus 2x as x approaches infinity, not 8. I'm just gonna put plus or minus so I don't have to write it twice. Alright, so first step. that square root's kind of annoying. Five minus 2x. I don't like that square root. Square root in this problem won't change our work, but it will make the answer a little messier. Let's first start with the first limit. In this case, the largest power of x in the denominator is just an x. So that after we take the square root, we will get an x. This is probably not something you're used to doing, but just remember that when it comes out of the square root, it needs to be an x, and the only way to have an x come out of the square root is to take the square root of x squared. And so that is what we'll need to factor out of the term under the radical. Here's the factoring work for this part. Really? Jeez, okay. I think I'll work on this tomorrow.